Good morning, everyone. Welcome to Mostly Math. It's a very special video, actually, since it's the first video after we've surpassed 100 subscribers on YouTube. So thanks so much, everyone that's subscribed so far. And please tell your friends, I want this to be the best math content YouTube has to offer. Let's get started. We are going to be discussing a particular property of the number 100 today to celebrate the occasion. It's a very elementary topic, so all of my subscribers can follow. Let's get started. Okay, the property relates to the sum of the cubes, which is a very familiar high school topic. We will be investigating the following identity. The number 100 can be written as 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. Feel free to check it for yourself if you don't believe me. And it can also be written as 1 plus 2 plus 3 plus 4 squared. Also check this one. And this is a special case of the following identity, which we are going to demonstrate in this video. We're going to be demonstrating the fact that the sum of k cubed as k goes from 1 to n is equal to the sum of k as k goes from 1 to n squared, which we know from elementary, high school, calculus, algebra actually, that this is simply n times n plus 1 over 2 squared. So we can see that although the identity involving 100 is cool, what's more cool is that it's a special case of the following formula for n equals 4. This tells us that everything we have up here as n goes to 4 is just 4 times 5 over 2 squared, which is 4 times 5 is 20 over 2, which is 10 squared, is 100. So we want to prove this formula in a few ways. I'll be showing the two most well-known proofs. I'll be doing induction proof, and I'll also be doing a proof involving a telescoping series. There are, of course, many other proofs involving contour integrals and all kinds of unnecessarily complicated structures like that. We'll just be discussing a few today. And like I said, this is a nice, easily accessible high school topic, so I expect all of you to be able to reproduce these proofs when we get to the 200 subscriber level, or whichever n corresponds most closely to 200. And I'll get back to you then. Okay, I'm going to rewrite what we're going to be proving. So we had sum of k cubed, k equals 1 to n, is equal to the sum of k equals 1 to n squared, which is n plus 1 over 2 squared. Okay, let's first prove this by induction, since that's every mathematician's first method of proof. I personally don't always like induction because it doesn't really give you any intuition as to why something is true, but everyone agrees that it certainly proves that it is true. So let's get started on that. Base case. We are going to start off with n equals 1. So we have this side, 1 cubed is equal to 1 squared, which is 1 times 2 over 2 squared, which is equal to 1. So the base case checks out. Now for the induction step, we're going to assume that it holds for a particular integer n, and then show that it also holds true for the integer n plus 1, writing the sum in terms of n and n plus 1. Let's get started. I'm going to assume this is true for integer n. Now we just evaluate n plus 1 and see what we get. Okay, so the sum of k is equal to 1 to n plus 1 of k cubed. Well, we can see pretty easily how we can write this in terms of the old sum from 1 to n, and the new sum since we just add the n plus 1 term. It becomes a sum from k equals 1 to n of k cubed plus n plus 1 cubed. Okay. And now we are in a perfect position to apply our induction hypothesis that this relation holds true for n. So we can just substitute this in, see where we go from there. This is n plus 1 over 2 squared plus n plus 1 cubed. And now you might be tempted to just expand n plus 1 cubed. Do not do this. It's messy and it doesn't get you anywhere that you can't go by doing what I'm about to do now. Let's go ahead and factor out common factor of n plus 1 squared. N plus 1 squared. This leaves us with, well, we have n over 2 squared from this term here. And then we have an n plus 1. And now we want to rewrite what's left by applying a common denominator. So this becomes, we have n squared plus 2n plus 2. Oh, sorry. The common denominator is 4. I do apologize. Common denominator is 4. N squared plus 4n plus 4 over 4. And now we're going to note that this is simply n plus 2 squared. Since when we do this, it becomes n squared plus 2 times n times 2 plus 2 times 2, which is 4. We still have a 4 down here. So it now becomes n plus 1 squared, n plus 2 squared over 4, which we can rewrite as n plus 1 times n plus 2 over 2 all squared, which is exactly what we want. Why do I want this? Because when we apply induction, we want to show that it holds for n plus 1. If we substitute n plus 1 into this formula, we get n plus 1 here, n plus 2, and the 2 stays there. So we're actually done. This is what we wanted all along. I think everyone can agree that this proof is very simple. Feel free to show your friends. I like it a lot. Let's go to a slightly more complicated but direct proof. An advantage of a direct proof is that you can use other assumptions besides the theorem itself to prove the theorem. So basically, if you use a direct proof, it tells you one reason at least as to why it might be true. So to begin, we're going to consider some telescoping series. Let me make sure I get them right. Very important. Okay, we're going to begin considering this series. We have the series k equals 1 to n of k plus 1 fourth minus k to the fourth. Okay, why the hell am I doing this, you might ask? We want cubes here. Why are you going to start with fourth powers? Well, the short answer is I've already done the similar proof for the other cases and it works out. The long answer is forthcoming. First, the strategy is to evaluate the sum in two ways. We are going to evaluating it directly by using the telescoping property, and we'll see where that leads. Okay. So, we are going to start with the k equals 1 term. When we do this, we have 2 to the fourth minus 1 to the fourth. Next term. 2 plus 1 is 3 to the fourth minus 2 to the fourth. Okay, we can see how we might get some cancellations. Yep, good. We got these two canceling so far. And the k equals 3 term. 3 plus 1 is 4. 4 to the fourth minus 3 to the fourth. And we get another cancellation here. We're going to continue on to the n minus first term. This gives me n minus 1 plus 1 is n to the fourth minus n minus 1 to the fourth. And finally, the last term that we're going to write is k equals n. This term is going to be n plus 1 to the fourth minus n to the fourth. Okay, so if we had observed the pattern indefinitely, we would have noticed that this term will cancel with some crap in there. This term will cancel with some other crap in there. And so would, oh sorry, these two actually cancel out. I do apologize. But this does cancel with some crap in there, leaving only this term left. So we have this term and we have this term. So this evaluates to, well actually I need another one. Yeah, no one anyways. Okay, so this one will be evaluating to n plus 1 to the fourth minus 1. Now, I actually am going to write this one out. But Brandon, you might say, n plus 1 to the fourth, I don't know how to do that. I only know how to do n plus 1 squared, n squared plus 2n plus 1. Well, it's actually pretty easy to generalize. You just use Pascal's triangle. The stupid way is to multiply n plus 1 by itself twice. Don't do this. I know I did this the first time. I tried to prove this in freshman year of calculus and I stopped halfway through. So don't do this. Instead, do what I'm going to do now. Okay. So Pascal's triangle starts off with the 1 up here. Then we have 2 ones there. We add these 2. To get 2, put 1s on the sides. We keep adding. 2 plus 1 is 3. And add more 1s. We keep adding. 3 plus 1 is 4. 3 plus 3 is 6. Get a 4. Get another 1. So this row actually tells us the binomial coefficients, which are all you need to evaluate n plus 1 to the fourth. So it tells us that it's equal to n to the fourth plus 4 n cubed plus 6 n squared plus 4 n plus 1, and then we subtract the 1 off there, so we can basically just get rid of both of those terms. Okay, this is a sum evaluated in one way. Now we're going to evaluate it in a slightly different way. We are going to do that by, how are we going to do that? Okay, this is the tricky bit. We're going to do that not by telescoping, but by evaluating this with Pascal's triangle. We're going to use the same Pascal's triangle, but instead of subtracting off the first term, we're going to subtract off the last term. So let's do that. Okay. It's also equal to this sum. Yeah. Just going to call this star, also star. For clarity. Okay, so we have the sum k equals 1 to n. Now, let's do the same thing. I don't even have to write it because I'm just going to replace n with k here, and then I'm going to subtract off the first term, this one here. So it becomes, we can try to do this right, yeah. So we have 4k cubed plus 6k squared plus 4k plus 1. We're summing from k equals 1 to n. We don't need Pascal's triangle anymore. Okay. Is this right? It's right. It's right. Okay, now here's why this proof is interesting. Because it allows you to use sums that we're going to assume. For the purposes of this problem, we're going to assume that we know how to sum k squared, k, and 1, and we're going to use it to sum k cubed. So I need to write down the sum that I'm going to use somewhere. Okay, so we know this sum of k squared is equal to, that's from k equals 1 to n. I always forget this one. n plus 1 2n plus 1 over 6. We're going to assume that we know this one. And we already know this one from the previous video. And this is the sum that we want. So we're going to set both of these two equations equal to each other as a function of n, and then solve for the sum as follows. Okay, this becomes 4 summation of k cubed. At this point, I'm going to stop writing the indices because it's annoying. Plus 6 times the summation of k squared plus 4 the summation of k plus the summation of 1. And now we can set this equal to this. So we're going to set this thing equal to this thing, and then solve for the summation of k cubed here. And I did this as follows. Tells us that 4 times the summation of k cubed, which we want, is equal to the thing we had before, n to the 4th plus 4n cubed plus 6n squared plus 4n minus the rest of this crap. Minus 6 times the summation of k squared. Well, the 6 goes away. n plus 1, 2n plus 1, plus 4 times the summation of k. Well, that was this here. So the 4 and the 2 cancel. So we get 2n plus 1. And then we get, oh sorry, this is minus. We're subtracting them off. Now we have the summation of 1, which is just n. Making sure I got this right. 4n cubed, 6n squared plus 4n. Yep. Okay, now let's see if I get this right. I'm not going to multiply any more terms. I'm just going to extract the terms directly. Let's see if I can do this. Okay. For the end of the 4th terms, there is only one n to the 4th term, isn't there? Yep, this is 3. Okay, now the n cubed terms. So this term is going to give me 4. N cubed. Okay, we get 1 from here. We got 2 times 1 times 1, which is minus 2. It goes minus 2 from these 3 terms here. Okay. Any other cubic terms in this expression? Should there be? 4 minus 2 is 2. So no, there's no more. Plus 2n cubed. Okay. We're done with the cubic terms. Quadratic terms. We're going to get 1 from here. We get 6. And, okay, so this is n squared. This is always there. There is a way to get a squared term if we go with these terms here. This yields us minus 1. Is that the only way to get a quadratic term? We'll come back to it in a bit. There's definitely one here. This one gives me a minus 2. 6, 5, 4, 3. Is that right, or am I missing one? There should be more. Okay. Well, I've messed up. I know what the answer is. I'm not going to be able to find it here. I know it's right. Sorry about that. I messed up. The answer is plus n squared. 6, 5, 4, 3. I'm missing 1. I don't know where it is. It's hard. It's hard. With practice, you can become better than me because I suck. And I'll just write down the rest of the answer at this point. Actually, that's it. There are no other terms. Why? Well, we have 4n here, and we have minus 2n, 4, 3, 2, 1. We're all good. This is the answer, n to the 4th plus 2n cubed plus n squared. Let's proceed. I'm sorry about that. It takes me about 5 minutes to get all the terms. Okay, and now the next step is to, again, factor out common factor of n squared. Let's see what's left. Okay, there's an n squared here. And we have, there's a 2n in that term, plus 1. Now this should look familiar since that's the only thing that we know how to multiply, at least some of us. N squared, n plus 1 squared, which is great. So now we have summation of k cubed, k is equal to 1 to n is equal to n squared, n plus 1 squared over 4, which we can conveniently write as a square. n plus 1 over 2 squared. Woohoo! We are done, everyone. Congratulations. Hopefully next time you try to show this proof to your friends, you won't make the same mistake I did. Perhaps multiplying out all the terms is better. Feel free to try it yourself both ways and see which one you prefer. And I hope you enjoyed this video about a property of 100, which is a special case of this particular identity. I think it's a really cool identity. There are, of course, many other interesting properties of the sums of powers involving fourth powers, etc., etc. There's also a general formula, which we're not going to talk about here. But if you enjoyed this, want to see some more, please subscribe and tell your friends so we can get to 200 subscribers pretty soon. I'll see you guys next time.